cross-section calculation, total cross-section calculation is basically a counting experiment. So by that you can calculate it. But then you have to compare with scattering when one of the particles not so compare the two results and then you will get some hints. Now yesterday we worked out one concrete example, that is scattering of electrons from a static charge distribution with total charge Z, and I write down the final result. Final result is, this is by the way a complete calculation. We are not doing anything anywhere. We are just taking a charge distribution of total charge Z and we are computing it, and it turns out that this d sigma d omega, this differential cross section is d sigma d omega point. Now this point means that I observe a scattering of E minus with a point-like particle having charge Ze, which is the total charge of the charge distribution. So d sigma d omega point means that this is the computable cross section when the electron scatters from a point particle of total charge Ze, and the result will be, this will be f of u square, where this f of u square is called the form factor, which is the Fourier transform of the charge density. Alright, and you can of course calculate it experimentally, because this is an experimental number. So this is measured by this ratio d sigma d omega observed, that is you have do a counting experiment and measure the number of scattered electrons within the solid angle d omega, where the solid angle is subtended by an area on the target, and divided by the theoretically calculated or the experimentally measured cross section if it is available, d sigma d omega point. But this now tells you a very, very important thing, that this tells you that f of q falls as q alright, also follows from the very definition of the form factor that f of q, because I did it yesterday, it goes to 1 for large, I'm sorry. Now these two simple information gives us a tremendous physics which will be very useful in many ways. First of all, remember this is not an approximation or anything, just the definition of f of q as I showed yesterday immediately tells you that because see, this is a Fourier transform, so it has in the integral e to the minus iq dot x. Now if let us say magnitude of q is very small compared to the charge large compared to the charge radius of the scattering center, then it is actually 1. You can see. So therefore, remember this is probably a very important step towards the next lecture. That is when q square is large, this is your scattering center. So this means the photon, actually the electron is interacting with the scattering center by exchanging a photon. Now when q is small, that means that the Broglie wavelength of the photon is large, and therefore it scatters from the entire charge distribution as a whole. Right? So in the other case, when q is large, then something like this, or maybe to make it more dramatic. It is of the same size. Then you see that the wavelength is small means it will scatter from part of the target. Therefore, it does not see the full charge of the target. That means its cross section should fall, and this fall is measured by the fall in the form factor. The fall in the form factor represents the fact that now at large q, your photon is not seeing, so to say, the whole charge of the scattering center, the extended charge distribution, and therefore you are getting a smaller cross section. Now borrowing terminology from optics, it is said that in this case the probe, which in this case is the photon. Probe means which is probing the structure of the scattering center. The probe cannot resolve the structure, and this means the probe resolves so this resolve is borrowed from optics. Now if you go to your textbooks on physical optics, you will see the well, it is not really physical optics, although the concept of wavelength is there. But anyway, if you go there, you will find that resolving power of a particular microscope increases if the, for example, if the lens of the microscope is large and the probe is having higher frequency or shorter wavelength. So it is a basically direct analogy. But now I I consider the special case.
So sir, just to draw the analogy, this first case is maybe an example of quasi-elastic process. The second case is a deep elastic process.
Yes, quasi-elastic means the
You are saying
direction of the momentum can change, but not the magnitude. In that case, momentum transfer will be typically small. The last discussion on this is on this topic. Now suppose consider the special that is, suppose the scattering center, the charge distribution arises because of the presence of many point-like particles. These particles are charged, right? So the charge, what you call a charge distribution, is essentially coming because there are particles inside the charge distribution. Example, nucleus. Nucleus is like a scattering center of total charge, say E. But this charge distribution comes because there are many protons inside the nucleus. Alright? In that case, if you want to really resolve this structure, that is, if you want to prove that there are point-like particles, it is a tough job, but you will always require a. So these dots represents point particles. So we need a high energy probe. By high energy means momentum transfer very large to resolve the structure. To give you an example from one of the most important events in the history of particle physics, let us say Rutherford scattering. What did Rutherford use? He used alpha particles. So they are energetic. In fact, they were the most energetic particles available in those days because there was no accelerator. Okay. So Rutherford had to depend on whatever he could get. And it resolved the nucleus inside the atom. Now this is not a mean task. Okay. For example, this probe could scatter completely from the charge cloud inside the atom due to the electrons. Remember, gold has 79. I didn't forget it one day. I keep on forgetting, but I remember now that Z for gold is 79. Okay, so there are 79 electrons, so it is basically a charge cloud. But because this is large enough momentum, the alpha particle, it could resolve the point-like structure inside the nucleus, and not only qualitatively, quantitatively the scattering formula, which happily coincides with the quantum mechanical formula. It was found that indeed there is a nucleus sitting inside the atom. But he needed the highest energy probe that was available in those days. Now the next discussion which we are going to talk about is basically, suppose the proton is made of quark. Now can we resolve the point-like quarks inside the proton by using a high energy probe? Now this is basically the subject of deep inelastic scattering and proton model I since a question was raised in the discussion after yesterday's lecture, let me spend 5 or 10 minutes on the form factors of electron-proton scattering. Now, as he said, this is a quasi-elastic scattering in the sense that the electron and the proton remains the same before and after the scattering. In this case, not only momentum, direction, but both magnitude and direction of the momentum changes. Had the proton been infinite mass, that is like a classical charge distribution, then only the electron would change its direction, but its energy will remain the same. But this is not the case. Proton has finite mass, so therefore both of them will scatter, although the recoil of the proton will be small. So I'll write down the final result.
So just one thing, when you mentioned here nucleus, example of nucleus, so you took only protons because they are the charged particles. But when you calculate the entire effect, since neutrons are also part of the nucleus,
they will contribute to the magnetic moment.
Yes.
They will contribute to that. This is exactly what I am going to discuss now. This is exactly what I am going to discuss now. Now the only thing is you don't get neutron targets. Therefore what you can do is, you can take a simple nucleus, let us say like the deuteron, and if your probe scatters, you subtract the effect of the proton, and that enables you to extract the form factors for the neutron. So, in terms of a Feynman diagram, don't worry too much about the word Feynman diagram, those of you who do not know it. This has a 4 momentum Ki, this has a 4 momentum Kf, and then I write the nucleon, but I put a blob here, just to remind you that we are not treating the nucleon as a point-like particles. So this has for momentum Pi initial Kf. Now from the calculation of yesterday, you can immediately guess that we are going to introduce a function. Unfortunately, this function will not be calculable as we did in the last. We could calculate the function as a Fourier transform of the charge density. Now in this case we cannot do it simply because of the fact that proton is a strongly interacting particle, and we cannot compute the effect of strong interactions on the cross-section perturbative. You can do non-perturbative calculations, but that is not the subject of the talk today. So now we will introduce form factors which are essentially unknown functions.